As I mentioned in the last video, the primary concern of this chapter is to determine whether an infinite series converges or diverges. And with these four examples that we just did, we were able to determine a little bit. 1 and 2, we seem to be able to answer definitively. 3, we have no idea. 4, we have some idea, but we're not really sure. So we're going to need some tools to help us answer the question, does this series converge or does this series diverge? And what we're going to learn is a series of tests, no pun intended, just a list of tests that we can apply to series to determine whether they converge or diverge. In fact, in the next 5 sections of this book, we're going to learn 10 tests to determine the convergence or divergence of particular series. Okay, today we'll learn a few of those. I think we'll learn 3 in this section. So 3 of the 10 we're about to see. Starting with the telescoping series. This is a fun one. The telescoping series is called thus because of the old-fashioned telescopes that you can imagine an old explorer is pulling out, and like it's all collapsing. They pull it out so that the two lenses are far apart from each other. They're looking up at the sky, and then when they're done with it, they collapse it down. And that collapsing action is mimicked in these telescoping series. A nice example of this is 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5. You're going to notice that the negative 1/2 and the positive 1/2 cancel out. The negative 1/3 and the positive 1/3 cancel out. Because most of the terms are gone, only one or just a finite value of terms are going to be left. We're going to be able to find the value to which this telescoping series converges. So my mantra here is always, when in doubt, expand it out. When we have two fractions that are being subtracted, you should, in the back of your head, think, aha, telescoping series. So I'll just expand this out and see what happens. When n equals 1, our first term is 1 over 1 minus 1 over 2. And when we look at when n equals 2, we get 1 over 2 minus 1 over 3. Now, wait a second. Hold on. Then we get 1 over 3 minus 1 over 4. This is exactly what we saw up here, right? This is this, okay? And the whole idea here is that the positives and the negatives cancel out there. The positives and the negatives cancel out here. The positives and the negatives cancel out here. In fact, everything's going to cancel out except for, in this case, the first term, namely 1. So this is 1 plus 0 plus 0 plus 0. This is just 1, right? So this series converges to the value 1. All right, so you can imagine that these must be kind of contrived series in order for that to happen, and that is the case. These don't show up all that often, but they do show up sometimes, and they're kind of nice. And what in the world is this thing doing in that same section as telescoping series? Because this is a single fraction, and this is 2 fractions. If there is only some way we can decompose this fraction to be the sum or hopefully difference of 2 fractions. Oh, wait a second, I gave it away, didn't I? Decomposition, right? We're gonna take this this fraction and we're gonna decompose it into its simpler fractions. So 2 over, well, that factors, that's a difference of squares. We've got 2n plus 1 times 2n minus 1. Right? So that's going to equal a over 2n plus 1 plus b over 2n minus 1. All right, so we'll go ahead and go through the process that we learned fairly recently. We've got a times one denominator. We've got b times the other denominator. And we can get 2an and 2bn, or not, 2bn. And we've got negative a and a positive b, so plus negative a and positive b. So this is 0 and this is 2 because we don't have any n's over here. We just have the 2. All right, so if negative a plus b equals 2, and if 2a plus 2b equals 0, in other words, if a plus b equals 0. Just take that and divide everything by 2. When we add these up, we end up finding that 2b is equal to 2, so b equals 1, which means that a equals -1, and therefore we can rewrite this original series as the sum. That's a terrible sum. So let me teach you how to do a better sum. Start by doing one bar all by itself across the top, and then pick up your pencil, and then that's going to make it a little bit better. Still not my favorite sigma that I've ever written, but it's better than that first for sure. All right, so a is -1, so I'll put a -1 on the top and 2n plus 1 on the bottom. B is +1, so I'll put a +1 on the top and a 2n minus 1 on the bottom. And suddenly this looks like a fraction, a sum of two fractions, one's positive and one's negative. If we're lucky, this thing will telescope. Or if we have contrived it properly. In this case, it's a contrived problem, right? But it works out. It's kind of fun. When n equals 1, we get our first term, which is going to be -1 over 2 plus 1 is 3. Plus 1 over, when n equals 1, we have 2 minus 1, which is 1. That's our first term. We're going to find our second term. That is going to be the next biggest odd number, right? So 2 times 2 is 4 plus 1 is 5. So we're going to get a -1/5. And this is going to become 4 minus 1, which is 3. So 1/3. And this is a little bit sad to me because we're getting the same answer as before, aren't we? -1/3 cancels with +1/3. -1/5 cancels with +1/5. -1/7 cancels with +1/7. The only thing that's left is 1. All right, so all telescoping series converge to 1. True or false? Of course that's false. But these two particular examples, our telescoping series converges to 1.